Whoops, did I already? Well, okay. So the first one, they're all true. Any questions about that, why they are all true? Which of the following best describes paracellular transport in the proximal tubule? Passive. Any questions about why that's true and the others are not? Which of the following are true? Just going to reveal the answers and we can discuss them if necessary. Any questions about those? Did you get, you were asking me a question about A. C, as in Charlie. Excessive reabsorption of glucose causes the clearance of glucose to be greater than 0. No. Excessive filtration of glucose would cause there to be clearance of glucose. The clearance of glucose is usually 0 because the urinary concentration is 0. We reabsorb it all. Well, we can't have excessive, it's not excessive reabsorption of glucose, it's inadequate reabsorption of excessive filtered glucose that leads to glucose clearance. Remember, clearance is excretion, and typically we excrete 0 glucose. Reabsorption is the opposite, not really, but it works against clearance. We reabsorb 100% of the glucose normally, so we clear 0 per milligrams of glucose, and so 0 urinary concentration of glucose will lead to a clearance of 0 mils per minute of glucose. Other questions? Okay. Again, which of the following is true? Just reveal. A and B. Any questions about those? Sophie.
Can you explain A?
A. The clearance of sodium is usually way less than the GFR because we reabsorb almost all the sodium. We reabsorb 99.5% of the sodium that we filter. And so the clearance of sodium is going to be a tiny fraction of the GFR. Remember, the GFR is measured by a substance that is filtered but not reabsorbed. Sodium is actively reabsorbed. Almost all of it is reabsorbed. So the clearance of sodium is way less than the clearance of something that is not reabsorbed, which is what defines GFR. Other questions? Your problem set this week will ask you to work with these and understand these concepts more. So actually, you have enough knowledge to answer questions 1, 2, 3. You have enough knowledge to answer questions 1, 2, and 3 already. Questions 4, 5, and 6. No, questions 4 and 5 ask you. Well, I think you're probably better off waiting until we have covered water reabsorption on Wednesday before you try to answer questions 4 and 5. And on Wednesday, we'll do our standard Wednesday drill where we'll meet in here, then I'll send you to Zoom locations. You'll work together on clickers and on the problem set for some time, and then we'll get back together to discuss it. And if you don't want to come back here, you can stay on Zoom. That's the Wednesday plan. Okay, let's move on to part 2. Part 2 today is to talk about bicarbonate and acid, both of which are complicated. And then we'll get into water. So here's a slide that I blanked out for you so that you could write in some words. Let's start here. Your textbook wants us to start here, but I think starting here is easier. We'll actually start in both places, kind of. How did bicarbonate? Okay, let's get oriented. Urine, apical membrane. The apical membrane should be wiggly, but it's not here in this cartoon. So urinary fluid, apical membrane, basolateral membrane, interstitium, blood over here. Capillaries. How did bicarbonate get into the urinary fluid? Nope. We're going to need carbonic anhydrase in a minute, but that's not how it got in here.
Is it like metabolic compensation for like respiratory alkalosis or acidosis?
It happens even in normal. We don't have to have acidosis, alkalosis, respiratory nor metabolic for bicarbonate to get into the urinary fluid. Remember, we have bicarbonate in blood. The concentration of bicarbonate in blood is, typically, arterial blood bicarbonate is 26 millimole. 26 millimole. Hint. How did bicarbonate get here?
Filtration?
Filtered. It's filtered. Bicarbonate is small enough to be filtered. So I want you to put the word filtered into that box, because it's important to realize that bicarbonate is filtered. What enzyme, Evan, catalyzes this reaction? Carbonic anhydrase. So put carbonic anhydrase in that box. This CO2 that was produced by carbonic anhydrase reaction with bicarbonate and protons. So bicarbonate and protons, association and dissociation, but sometimes there's association. Carbonic anhydrase accelerates this reaction. So both of these arrows should be reversible, of course, because everything is reversible, but this reaction is accelerated. If there is carbonic acid, it will be, the reaction to break it down into water and CO2 is accelerated by carbonic anhydrase. This CO2, is it confined to stay in the urinary fluid? No, it diffuses everywhere. It diffuses into the cells that it's next to. Well, this CO2 can go here, right? I mean, this cell is the same as this cell. So CO2 is not going to flow upstream, but this cell is the same as this cell. So this CO2 gets into this cell and then starts this process. The point is that there is carbonic anhydrase that is expressed in the lumen of the tubule. It's actually anchored to the apical membrane. But it's enzymatically active, not in the cytoplasm, but in the lumen to catalyze this reaction. There is also carbonic anhydrase inside the cells It's a different variant of carbonic anhydrase. That now, since this CO2 is this CO2, for all practical purposes, this carbonic anhydrase catalyzes this reaction and it dissociates, right? You know this chemistry. There's a proton and there's a bicarb ion. Now we've got some transport to do. What from the previous hour in this class allows you to unpack this process? There are two transport proteins that we have talked about in the previous hour that are embedded in this process. What are they? Somebody name one of them.
The sodium bicarbonate co-transporter.
The sodium bicarbonate co-transporter is one of them. So right here, sodium bicarb, or NaHCO3 co-transport. And what's the other one? The one that I kind of glossed over, but I said we're going to need it when we get to bicarb. That's where we are now, bicarb. Sophie?
One was chloride.
A chloride bicarbonate exchanger. So put in this box two transport proteins that are in this cartoon embedded in this one thing here. Sodium bicarb co-transport and chloride bicarb exchange are both happening here. And similarly, there are two things that happen here, one of which I've told you about. So the one that I've told you about is what? That's embedded in this process.
So,
The sodium proton exchanger. And the one that I haven't told you about is that in the apical membrane, there is a proton pump, a proton ATP base. What are you doing? It's not thunder. It's not, there's no storms happening today. They're rolling something around. So we have a proton pump, a proton ATPase that is pumping protons, and we have the sodium proton exchanger that's bringing sodium in and pumping protons out. So your handout should look something like that. Oh, I forgot. You know that carbon dioxide, the partial pressure of carbon dioxide is around 40 for a normally respiring person. Okay? So we've set things up here now. So how do we see bicarbonate reabsorption? Bicarbonate is filtered. It is converted into CO2. CO2 is converted into protons and bicarb. Bicarb is pumped, and protons are pumped to help make the CO2. So bicarb is actively transported, but there's this intermediate step of turning it into CO2 and letting CO2 diffuse. Where did the pumping of bicarb come from? The sodium bicarb co-transporter. And why is that active? Because it's using the sodium gradient. Well, no, it's not using the sodium gradient, it's using the bicarb gradient. So bicarb is bicarb the activeness of this transport, some of it comes from here, and some of it comes from here. This is where the ATP, either directly or non-directly, was involved in this process. That's tricky, but what I want you to know, the story, filtered, becomes CO2 because of this luminal expression of carbonic anhydrase, turns it into CO2, CO2 is converted into bicarbonate, which is exported and therefore reabsorbed. That process depends on a proton being available for this reaction. So let's move on to the next. I want you to work with this a little bit. So here we are normally. And we are normally recovering, reabsorbing bicarbonate in order to keep bicarbonate concentration around 26 millimole. And that helps keep our pH 7.4. So let's talk about metabolic acidosis, right? Okay, I'm just picking one at random. Metabolic acidosis, exercise, lactic acid. Your muscles are producing acid metabolically, you're getting metabolically acidotic. Okay, what does your respiratory system do? Your respiratory system compensates by breathing more ventilation, more respiratory frequency, lowers the PCO2 in order to make a compensation of the pH, right? So you know that. You exercise, you breathe more. You're aware of that compensation. But the other compensation, so let's say you're running a marathon and you're running for hours. In addition to the respiratory compensation, there could be renal compensation to try to recover pH normally, right? So there's the respiratory compensation and a metabolic or renal compensation. How could we increase plasma bicarbonate? That is to say, how could we decrease the excretion of bicarbonate, right? If we decrease the excretion, if we increase the reabsorption, we will increase plasma bicarbonate. So the question is, how does the body respond to increase reabsorption? It does that by changing the expression of the key proteins that are important for bicarb transport. Increased expression of these transporters. Increased expression of carbonic anhydrase. Increased expression of this transporter. Increasing expression of these processes leads to more bicarbonate reabsorption, which is renal compensation for, let's say, muscular acidosis. Okay. Let's do respiratory acidosis, hypoventilation. How do we reabsorb more bicarbonate? How do we reabsorb more bicarbonate in respiratory acidosis? Same thing. Is that what you just said? Same process, right? The body responds to low pH, whether it is metabolic or respiratory, to increase the reabsorption of bicarbonate. Does this make sense from an acid-base perspective? Well, yeah, remember that bicarbonate is a weak base. So if we are acidotic, we want to have more base, and we want to excrete less base. So I'm going to ask you to work with these concepts in a couple of clickers. Let's take a 5-minute clicker interval and ask you to work on a couple of clickers.